Now that we are done with our studies of sequences, we're going to turn to series, which is what we're going to be studying for the rest of the course. So if we start with a sequence AN, and we start adding together the terms, so let's say the first term of the sequence with the second one, with the third one, and so on, until a certain point. So we add n numbers, and that makes no problem, it makes sense. We add finitely many numbers, and so we get some value. But what if we keep going, and we keep adding numbers ad infinitum? Well, then the question of whether this makes sense or not comes up. And you can easily see on simple examples that it will not always make sense. If, for instance, you consider the sequence whose nth term is n, and you start adding all the terms together, so you add 1 with 2 with 3 and so on, then you keep adding numbers that are larger and larger, and of course this is never going to add up to a finite number. So this wouldn't make sense, and in that case we're going to say that the series is divergent, even though here it is waving hands a little bit because we didn't really define what a series is yet. But you see that this infinite sum would not make sense. How about this infinite sum, 1/2 plus 1/4 plus 1/8 and so on? So I add the terms of the sequence 1/2 to the n, and I try to add them all together. Would that make sense? Well, this is related to a historical philosophical problem, one of the paradoxes of Zeno that you may have heard of. Zeno argued that motion is an illusion, and one of the paradoxes that he pointed out to illustrate that is that if, for instance, you want to walk to a wall, then you first have to reach half of the distance, cover half of the distance that separates you from the wall, but then you still have to, at the next step, to cover half of the distance that remains, which is 1/4 of the initial distance, and then when you're at this point, you still have to cover half of what remains, so that's half of 1/4, 1/8 of the original distance, and so on. And so you add up these fractions of the original distance that you had to cover, and while you get the sum of all of these distances, 1/2, 1/4, 1/8, 1/2 to the n, and you keep going. So there is a paradox here for two reasons. One is that you have to deal with infinitely many steps, and that is not something, some philosophical objection may remain to that. However, in terms of the paradox arising from adding infinitely positive numbers and arguing that this might not add up to 1, then we will see that there is no problem to that. This adds up to the distance 1 that we have to cover. Indeed, if you represent geometrically 1 by a square of size 1, then 1/2 can be represented as the rectangle with one side of length 1/2 and the other one of length 1. 1/4 can be represented as a square of size 1/2. 1/8 as a rectangle with one side of length 1/2 and the other one of length 1/4. And we can keep going this way, 1/16, 1/32, and we keep going. And we keep adding these smaller and smaller rectangles, and you see that geometrically it looks like we're just going to gradually fill in our original square of area 1. So this suggests that this infinite sum adds up to 1. Let's try to confirm that algebraically with something a little more analytical. Let me call S1 the sum of the first term alone. So I just take the first term, 1/2. And then S2 is the sum of the first two terms, 1/2 plus 1/4. I'm adding finitely many terms, so this makes sense. That's 3/4, which, as you can tell, can also be written 1 minus 1/4. Then S3 is the sum of the first three terms, 1/2 plus 1/4 plus 1/8. That's 7/8, which I can write 1 minus 1/8. And I can keep going this way and denote by S indexed by n the sum of the first n term in my sequence 1 over 2 to the n. So I will call that the sequence of partial sum, the sequence of general term Sn. It's a sequence of partial sum for the sequence 1 over 2 to the n. So this 1/2 plus 1/4 plus 1/8 and so on until 1 over 2 to the n. Judging by the first three terms, S1, S2, S3, it looks like it might be something that we can express as 1 minus 1 over 2 to the n. So let's try to verify this. We want to show that for every n, Sn is 1 minus 1 over 2 to the n. When we want to show a property for every n, one way to do that is by induction. So we proceed by induction. S1 is 1/2, which I can write 1 minus 1/2, that's 1 minus 1 over 2 to the 1. So the property checks out for n equal 1. Then we have to show that if I know that the property is true for a certain n, in other words Sn, the sum of the first n terms, can be written 1 minus 1 over 2 to the n, then it is true for the next n. In other words, the sum of n plus 1 terms is 1 minus 1 over 2 to the n plus 1. So I'm going to start from the sum of n plus 1 terms, so I add 1/2 with 1/4 and so on, and then I have 1 over 2 to the n and one more term, 1 over 2 to the n plus 1. But adding the first n plus 1 term together is really adding together all the first n terms, and then this additional term 1 over 2 to the n plus 1. So it's really Sn plus 1 over 2 to the n plus 1. But our assumption here is that Sn can be expressed as 1 minus 1 over 2 to the n. So I can replace Sn by this expression, and I get 1 minus 1 over 2 to the n plus 1 over 2 to the n plus 1. Well, and in the last two terms, in this sum of three terms, I can factor out 1 over 2 to the n. It is multiplied by negative 1 when I get this negative 1 over 2 to the n, and it is multiplied by 1/2 in 1 over 2 to the n plus 1, because when you have 2 to the n plus 1, it's really 2 to the n that you multiply by 2. So 1 over 2 to the n plus 1 is 1/2 times 1 over 2 to the n. That means that doing this factorization, this is what we obtain, and in the parentheses I have 1/2 minus 1, that's negative 1/2. When I multiply it by 1 over 2 to the n, I get negative 1 over 2 to the n plus 1. And so we've obtained that the property is true for n plus 1. So by induction, that proves that Sn is indeed equal to 1 minus 1 over 2 to the n for all n. And if this is true for all n, then we can look at the limit when n goes to infinity. And if n goes to infinity, 2 to the n goes to infinity, 1 over 2 to the n goes to 0, and Sn as a sequence has limit 1. Think of what this sequence of partial sums Sn is. You add all the consecutive terms of your sequence 1 over 2 to the n up to a certain point, and then when you look at the limit, you're letting the number of terms go to infinity. So essentially this is exactly what we want to consider the infinite sum. So this infinite sum that we're going to denote with a sigma sign, where we say that the index n starts at 1 and goes to infinity, this series, this is what we're going to call the series of 1 over 2 to the n, is equal to 1, because by definition it is really just a limit of the sequence of partial sums. So, as I mentioned before, Zeno of Ela, which was living quite some time ago, as you can see, expressed various paradoxes about the impossibility of motion and the fact that motion is an illusion. And while some aspects of these paradoxes remain startling, some aspects are clarified by this viewpoint in terms of infinite series. In terms of adding infinitely many terms, you can clarify some of the problems that arise in these paradoxes. Now, more generally, if we have a sequence, an, that we're going to call the sequence of terms, that's what we're going to add together, We can first associate another sequence, which is a sequence of partial sums. Let's denote that Sn. And Sn is the sum of the first n terms of my sequence of terms. So I add a1 with a2 and so on until an. With a sigma sign for the sum, it's the sum from 1 to n of the ai's. And the series is going to be the infinite sum, which is by definition the limit of the sequence of partial sums. So when I keep adding more and more terms. And we're looking at the limit. So of course this may or may not make sense because this limit may or may not exist. We're still going to use the notation, the series from 1 to infinity of the ANs or of the AIs before we know whether the limit exists or not. So we're going to talk about a series that is convergent when the limit exists and divergent otherwise. Of course, in the case where it's divergent, the notation itself doesn't make a lot of sense, but as a convention we're going to still, as a convenient abuse of notation, we're going to still write this infinite sum before we know whether it makes sense or not. When it is convergent, it means it makes sense, it is a finite number. When it is divergent, well, this is all we can say about it, is that this infinite sum doesn't really make sense. A standard question that we're going to investigate from different viewpoints is, given such a series, is it convergent or divergent? One way to think of that is a sequence of partial sums of the ANs a convergent sequence or not? We'll see that we can sometimes justify that the series is convergent, but without knowing the exact sum, in other words, without knowing what the limit of the sequence of partial sums is. But usually we'll be able to estimate it. So we'll see various examples of that sort.